recording, then students who miss the class today will have something to refer to after. Okay, so today we plan to cover section 8.2, testing a claim regarding population proportion. Firstly, population proportion is represented by the notation P. The focus of today's class is to test a claim regarding population proportion P. Mainly, we are going to go over 3 examples, not a lot, okay, just the 3. But we are going to go through the three examples in great details, So the procedure to test the claim regarding population proportion is called normal approximation method. So some requirements must be satisfied before we actually apply the method. Let's look at the requirements right here. Technically, every time you apply the procedure, before you apply the procedure, we have to double check, go through those requirements, make sure those requirements are met. We have the following 3 requirements. First requirement, the sample has to be simple random sample. Simple random sample is a very good sample. It's representative, not biased. The reason we have this requirement is to make sure the procedure is replicable. Like you do a research, you have to make sure your research can be repeated by other researchers, and you guys have the same result if you go through the same process. So that's the first requirement. Second requirement is we have a binomial distribution in the procedure. The conditions for a binomial distribution are satisfied. Yeah, we have 4 conditions for binomial distribution. They are those 4. There is a fixed number of trials, let's say n trials, and n is a fixed number. All the n trials are independent. They do not affect each other. Each trial has 2 categories of success and failure. The outcomes of each trial can be classified into 2 categories, success and failure. And the last one, the probability of success for each trial remains the same. So that's the second requirement. We have a binomial distribution. The third requirement actually is the requirement for normal approximation. We require the number of success and the number of failures must be at least 5. Okay, yeah, n times p. N is the sample size. P is the probability or proportion of successes. So n times p actually is the number of successes. The number of successes at least 5. Same way as the number of failure has to be at least 5. When those 2 conditions are met, then we can use normal to approximate binomial. All right, yeah, those are 3 conditions. Technically, we should always go through them to make sure the procedure have all the 3 conditions met. And let's go to our first example. In a study of cell phone usage and brain hemispheric dominance, an internet survey was emailed to 6,957 subjects randomly selected from an online group involved with years. There were 1,322 surveys returned. Use a 0.01 significance level to test the claim that the return rate is less than 20%. Use the p-value method and use the normal distribution as an approximation to the binomial distribution. Okay, so that's the content of this problem. We are going to use two different methods to test the claim here. All right, the first method is called a critical value method. Years ago, I taught Triola's book. Triola is the author of our textbook. Yeah, the version I taught is different from our book. Yeah, at that time, the method is called the critical region method, and now he changed it to critical value method. It's the same thing. Okay, same thing. The first method is called the critical value method. This method is treated as a traditional method for hypothesis tests. Second method is called the p-value method. And those two methods are equivalent. When we say two methods are equivalent, we mean the two methods would always give us the same result. Yeah, that's what it means. Yeah, the two methods are equivalent. Okay, so let's see, how do we start the process? Okay, yeah. So the very first thing always to identify the OC. Yeah, anybody can guess what does OC represent? I think I used it last time. Yeah, what does OC represent? Well, if I do not use the initial, original claim. Yeah, our hypothesis test always start from identifying exactly. Thank you, Miranda. Original claim. Sometimes I would write OC. Okay, just to save time for convenience. Okay, let's see what is our original claim here. There's a sentence here. Test the claim. Yeah, what's the claim? That's the original claim. That the return rate. Yeah, the return rate is our proportion, okay? P or percentage P is less than 20%. Yeah, so that's our original claim. And we are going to write the original claim in a symbolic form. Symbolic form of this claim is P is strictly less than 20%. Yeah, normally we don't really write 20%. We would convert the percentage to its equivalent decimal. Yeah, we know 20% is 0.2. Yeah, we use the decimal most of the time. So that's the very first thing. Identify the original claim and then write the original claim in a symbolic form. And that's it. Okay? And then after we have our original claim, we are going to determine H sub 0 and H sub 1. We went over those concepts last Thursday, right? Yeah, anyone remember the name of H sub 0 and H sub 1? How do we call H sub 0? And what's special about H sub 0? How do we call H sub 1? And what's the relationship between the three things? Yeah, exactly. H sub 0 is the null hypothesis. H sub 1 is the alternative hypothesis. Very good. And remember a very, very important thing about the H sub 0, the null is the null always, contain equal sign. Always equal for null. Okay, I understand what you mean. Yeah, thank you, Kelly. Yeah, the null always contain equal sign, okay? So in this case, H sub 0, the null hypothesis would be P equals 0.2. All right, our null hypothesis would be the return rate equal to 20%. And what about H sub 1? How do we know H sub 1? Remember, the original claim must be the same with one of the two hypotheses. Okay, yeah, the original claim must be either the same with H sub 0 or the same with H sub 1. Since in this case, original claim is different from H sub 0, then the original claim in this case has to be the same with H sub 1, right? So our H sub 1 alternative would be P is less than 0.2. Okay, yeah, use those rules or connections between those three things to determine H sub 0 and H sub 1. All right, after we have our two hypotheses, the next thing we do is to determine what type of test we're going to apply. We look at H sub 1 to determine, look at the alternative hypothesis to determine if the test is a left tail or right tail or double tail. Double tail we just to call two-tailed test. In this case, so if your alternative is let's use 0.2 just for convenience, okay? Is the proportion less than 0.2, then we're gonna have a left-tailed test, okay? Left-tailed test. Suppose our H sub 1 alternative is P equal to 0.2. Of course, not this case. I'm just saying suppose, all right? Then we have a two-tailed test. We're gonna have a two-tailed test. And suppose our H sub 1 is P bigger than 0.2. Then we're gonna have a right-tailed test. Then you can answer in this case what type of test we are going to have. Look at our alternative. That's the general rule, okay? Depends on the alternative, the symbolic form of the alternative hypothesis. Since we have P is less than 0.2, of course, we are going to have a left-tailed test, right? We're going to have a left-tailed test. That's the thing we need to do right after we have the H sub 0 and H sub 1. And then now we know we're going to have, the spell is wrong, right? ED, tailed, left-tailed test. Once we know we're going to have a left-tailed test, we're going to graph the line, graph the curve. Let's see what kind of test statistic we're going to have, okay? We covered that on last Thursday. Let's see the table here. Test statistic for population proportion. For population proportion, the test statistic we are going to use is this z-score. Z equals p hat minus p over all over rho pq over n. Okay, since the test statistic is a z-score, we are going to have a z-test or left-tailed z-test, more specific for our problem. So here, let me write it down. We are going to have a left-tailed z-test. So the curve we're going to have is going to be a standard normal curve. If I have to write a very kind of accurate curve, it's going to take a little bit of time. It's not perfect. Or if I draw the curve faster, sometimes I have a very fat tail. Let me draw slower. So this is Z curve, okay? Remember Z curve corresponds, Z curve is just different name for standard normal curve, all right? We have left-tail test. That means our alpha, our significant level alpha is on the left tail. All right, yeah, so here z sub alpha, yeah, we know it's gonna be a negative number because the z curve is centered at 0, right? Yeah, we know it's gonna be a negative number. So this region, too thick, yeah, this region gonna have area alpha, which is 0.01 in our case, is predetermined. All right? And you know what? That red region, shaded region, is a critical region. It is the critical region, all right? Yeah. The shaded region, let me write it down. The shaded region, is the critical region. All right? Yeah, critical region. Since alpha is predetermined, the critical region actually is predetermined because critical region depends on alpha. Well, our z-score, because the first method is called the critical region method, right? Yeah, our z-score is p hat minus p all over square root pq over n. Yeah, seems very complicated. Yeah, p we know. P here is the population proportion. Of course, we don't know the exact value, but we claim the original claim is the P is less than 0.2, right? So P here actually is the proportion in the claim. So P here is going to be 0.2. P here is going to be 0.2. If we know P is 0.2, then Q as the complement of P is going to be 0.8. N is the sample size. 6957. 6957. Yeah. So that's the sample size. And what about p hat? P hat is the sample proportion. Okay. P hat is the estimation of the population proportion. In this case, is x over n. The number of the number of successes over sample size. How many returned? 1322. 1322. 1,322 over 6,957. Yeah, I normally don't really keep going to, to convert this fraction to decimal or whatever. I would just put it in the calculator. I'll tell you how, okay? Yeah. So if we plug in all those values, and we will have a z-score, right? Yeah. Yeah, how about let's see what's the z-score equal to. You have your calculator ready, guys? Yeah. So this is the how do I plugging in. Firstly, in the main page of the calculator, I would enter 1322 divided by 6957, and then enter. I would have a decimal, but I don't care what's the decimal. Is the decimal equivalent to the fraction I just entered, right? That's p hat. That's p hat. Yeah, and then I'm going to enter minus 0.2. The answer, you would see answer minus 0.2. That gave me negative. Yeah, it makes sense because we're doing left tail test, right? Yeah, negative 0.0099755642. Yeah, make sure you are having the same thing with me. Yeah, and then what I do, and then I enter divided by, and you will see answers slash, right? And then what do we do? And then you enter second x squared, and you would see a square root. So right now you should have answer slash and square root. And you probably have a box here is blinking. You are going to type the things in the box. All right, yeah. And in the box, what do we gonna have? We're gonna have 0.2 times 0.8. Sometimes if the number is very convenient, I'll just quickly get it done. 0.2 times 0.8 is what? 0.16, right? 0.16, yeah. Enter 0.16 divided by, yeah, make sure you are still under the square root, divided by the sample size. Sample size is 6,957. And then you are going to push this key, you know, and let the indicator go outside the radical, and then enter. Yeah, let me know what you have. Let's see if we have the same thing. I hope I'm clear about that, the process. When you spend more time with the calculator, you would have your own way to talk to the calculator, right? Awesome. Yeah, same with me. Yeah. And I'm not going to round it. Yeah, I'll just keep the number unrounded. Yeah, as precise as possible. Thank you. Thank you, Kelly and Miranda. Yeah, you guys all have the same answers with me. Yeah, but as I said, I'm not going to round it. I'll write a number here, whatever I have on the calculator, okay? -2.0801, 0801, 2042. Yeah, we should have more, but the calculator doesn't fit all the digits, but this is good enough. This would be good enough. 92.08012042. Okay. All right. We have the precision available. Dustin, do you have any question? I saw
No,
you.
no, I accidentally hit the key and. Yeah,
oh, it's okay. It's okay. Yeah. Okay. So what is this called? This is called what? What is this? What is this? The Z here? It's called test statistic. All right. Yeah. That's our test statistic. It completely depend on our sample. Of course, P here is from the claim, but you know, mainly depends on the sample. And Z sub alpha, in notation wise, they are so similar, right? Yeah, but they are different. Yeah. Z depends on the sample mainly. So our test statistic. And Z sub alpha is our critical value. Let me write it down. Critical value. The critical value separates the critical region and non-critical region. Yeah, the blank region, this part, yeah, that blank region is non-critical. The red region, red shaded region, that's the critical region. Yeah. So now what do? We are going to see where does Z, the test statistic, fall in the on the curve. All right. Yeah, but we have to figure out what is the critical value. Yeah, we just get a test statistic. How do we figure out the critical value of Z sub alpha? Let me double check the significance level. Yeah, 0.01. Yeah. So we are looking for the Z sub alpha. The critical value is a value, right? The value separate the critical region and non-critical region. So, and also this is standard normal distribution. Yeah, the function we are going to use, we're not using the table, okay? The function we are going to use in the calculator to figure out what is Z sub alpha, the critical value, is going to be inverse normal, okay? Yeah, let's go to second verse. Yeah, at this point, you should be very familiar with what I'm talking about. When you heard I say second verse, you know we're going to have a list of distribution to choose from, right? As I mentioned, we are going to choose inverse normal. Inverse normal. Area. The area always have to be the area to the left, area of the region to the left of the value we are trying to figure out. So in this case, 0.01. And keep mu as 0, sigma as 1, and paste. And my critical value, yeah, same thing. I'm going to keep whatever I have here, right? Yeah, negative 2.326, negative 2.326, 347,877. Do you have the same thing, everybody? The critical value? Remember, how do we interpret this score? Yeah, this score, you got a error message. Yeah, when that happens, we should try again, right? Clear everything in case the history data is disrupting or the current data. I have a negative 1.28. Let me double check mine. Let me double check. So second verse, inverse normal. The area is 0.01, no problem. Mu is 0, sigma is 1. Paste. Yeah, I got a negative 2.326,347,877 again. And would you like to try again? The area is 0.01 because it's a left tail test. So all the significance fall on the left tail. Oh yeah. 0.01, right? 1%, very tiny. Yeah. All right. Do you think we can proceed here? Any questions so far? No? Yes? Okay. So that's the critical value. Do you remember what does Z means in previous chapters? Z is the relative standing, right? Yeah, Z describes the relative standing. That means the critical value is around 2.3 standard deviation below the mean, and whatever to the left of that critical value, they are seen as significant low. All right, yeah. So now we have our critical value, and we also have our test statistic, and we are ready to apply the first method, critical value method or critical region method. All right, to apply critical region method, we need critical value, we need the test statistic. The order doesn't matter. If earlier we do z sub alpha first and then find the z value, the test statistic doesn't matter. Yeah, the order really doesn't matter. So now what we have both, right? We have the critical value z sub alpha and we have the test statistic z. We're gonna compare them. Yeah, we're gonna see where is z in the graph. This is z sub alpha. Then where is z in the graph? Z is negative 2.08. Is z to the right of the critical value or to the left of critical value? They are both negative. Yeah, look at their absolute value. Should the one with smaller absolute value closer to 0? So where is the test statistic? Negative 2.08. Where is it? I need to use a very bright color here. Do you agree? It is to the right here. Negative 2.08 is to the right of the critical value, right? Yeah, that color is bright. To the right, yeah, to the right of the critical value. That means what? That means the test statistic does not fall in the shaded region, does not fall in the critical region. It falls in the non-critical region, right? When that happens, we are going to say fail to reject the no. Yeah, we firstly have to make a decision about reject a no or fail to reject a no. No. We do not use, be careful, we do not use accept. We need to be very careful with this word. Fail to reject doesn't mean we accept. Fail reject just means our sample, we only have one sample, right? Our sample failed to reject a no. That's all it happened. It doesn't mean we're gonna accept it. In order to accept it, that take more effort, right? You see the difference. Yeah. If suppose the test statistic fall in the critical region, then yeah, since it fall the critical region, that means the rare event occurs, right? Yeah. The critical score, the critical value actually is the criteria for how rare is rare. Here means that 1% is rare. Yeah, if it's lower than 1%, that means a rare event occurs. Remember the logic behind the test hypothesis test I gave you on Thursday. Yeah, you have an assumption. Yeah, all the procedure assume our hypothesis tests all start from assuming H sub 0 is correct. All right, yeah, and then we turn if suppose the test statistic fall in a critical region, that means a rare event occurs, right? Yeah, rare event occurs. That means the assumption is wrong, because we assume by the rare event rule, we assume in one trial the rare event not supposed to happen. Like you never buy any lottery and suddenly you go to buy lottery and become millionaire. We assume that will not happen in one trial. So if the test statistic fall in the critical region, we are going to reject the no. Means our assumption is wrong, is false. But in our case, it didn't happen, right? Our sample, the test statistic, fall in a blank region. Then we would conclude we fail to reject the no. Again, you don't accept, you just say fail to reject. Okay, yeah, let me highlight this part, and we're gonna go back in a moment later. So that's the critical region or critical value method. In order to apply the critical value method, we need two things. One is the critical value, the other is the test statistic. Yeah, any question about how do we find the critical value and how did we find the test statistic and how did we compare them, right?
So Professor, you had that table for like proportion and mean and difference of test statistics. You mentioned that we'll be able to request certain things. Mm-hmm. Will that table be available, or do we need to know that information?
If you request, I'll include it.
Okay.
Yeah.
Great. Thank
and
you.
Later, no problem. Yeah, you will see you probably don't need a formula. You will see you probably don't need it. And by the way, why today I only prepared 3 examples? Because we need at least one section to really apply the process like manually in detail. Then you understand what happened. And later you will see we can use a calculator to get it done very quickly. you would say, why did we do that? Yes, we at least have to do this at least a few times. Okay. Yeah, I'll tell you. So this is the critical value method, and we decide to fail to reject the no. All right. And second method is the p-value method. And what do we do with the p-value method? And first, let me write the z. So this is z, right? Yeah, this is z. The purple, this here. Z equals -2.08012.042. Yeah. How do we manually to compute the p-value? P-value is a probability. Okay, very important. It's called a p-value, but it's not actually a value. It's a probability. What area? Is the area to the left of this purple? Oops, not purple. So is the area to the left of the test statistic in the graph. All right. How do you see this? Like a very bright purple line represents the test statistic, negative 2.08. Yeah, the p-value is the probability, yeah, that the score, this score, less than negative 2.08, 012042 is that area. Okay, yeah. Okay, very good. Thank you. Yeah. Well, since the p-value is a probability, and we are looking at a z distribution, the standard normal distribution. So, what function we should apply in a calculator to find the probability? We're going to use a normal CDF, right? Yeah, normal CDF. So let's go to second vars and select normal CDF and lower. Yeah, so here I'm going to write, then you know we're going to enter what the values for all the entries. So for the lower, you enter a negative EE 99. Yeah, we have talked about that, right? The upper, you are going to enter negative 2.08, 01, 2042, and mu keep as 0, sigma keep as 1, and you paste. We have done this a lot of times. Yeah, let's see. My calculator has a -1 EE 99 there already every time I use this function. And I only need to enter the upper bound, which is a negative. Be very careful. Do not use the minus sign. Use the key on the bottom right of the calculator, the negative sign in the parentheses. Okay, do not use the minus sign. Negative 2.08, 01, 2042. And mu equals 0, sigma equals 1, paste. So the probability I got, the probability must be bigger than 0.01. Actually, by even just look at the graph, you know, right? Because z is on the right of z sub alpha. Of course, the area to the left of z is bigger than the area to the left of z sub alpha. Yeah, the exact value. Yeah, sometimes the question asks you to find the exact value. My exact value is 0.01. It's pretty reasonable. It's a little bit bigger than 0.01. 0.0187, 57, 757, 1793. Yeah, that's my p-value. Okay, let me know, do you have the same thing? For p-value method, that's how do we find the p-value manually. Yeah, we still have to have the test statistic, by the way. We still have to have the value perfect, same. And what do we do? How do we make the decision about the no? We're going to compare the p-value, with our significant level alpha, determine the significance level, how rare is rare, 0.01. Okay, and I want you please remember this very catchy sentence. Yeah, p-value is low, p-value is low, no must go. If p-value is high, p-value is high, no must fly. Yeah, I guess once you read a few times, you probably one time you would remember these two sentences. P-value is low. How low is low, right? It compare with the significance level. If the p-value is lower than the significance level, then no must go, means we're going to reject the no. Must go, right? Yeah, reject you. You have to go. And if the p-value is high, means higher, bigger than the significance level, then no must fly, like a no is happy. Fly, right? Means you failed to reject no. So in our case, you tell me, guys, when we compare p-value with alpha, yeah, is p-value low or high in our case? Our p-value, yeah, when you look at the graph, you actually already know, right? Yeah, exactly. P-value is high because the p-value is the area of the region to the left of z. It is bigger than 0.01, which is the area of the region to the left of z sub alpha, because z is to the right of z sub alpha, so it has more area, bigger region, bigger area. So must fly. So we fail to reject no. You see that? Yeah, the two methods always equivalent, always give you the same result. Both methods we apply gives us the decision we are going to fail to reject no. All right, not done yet. Yeah, the two methods give us the decision about a no, but you know, a no didn't even exist in the original problem. We are testing the original claim. Then how do we make the conclusion about the original claim? Let's look at that. We're gonna fail to reject no, right? Yeah, we decide to fail to reject. When we fail to reject no, would you support H sub 1, which is the original claim? When you fail to reject no, would you support? You fail to reject no means that there's a chance the no is right. You know what I'm saying? So you say we have no sufficient evidence to support the original claim. All right? Yeah. So when you go to MyLabMath and doing the homework, and the last step always is to make the formal conclusion. I have a table for you here. I have a table for you here. You know, the long time ago, years ago, the older version of the Triola's book, they have the table. I typed this one, okay? I actually typed this table. I couldn't find my original note from years ago. And I look at the new book, the new version, it did not have the table. They have a flow chart, and I do not like the flow chart, so I made the table. It's more convenient. So here in our case, the original claim is the same with the alternative, and we end up with both methods give us the result. We need to fail to reject no, right? So the formal conclusion is here. There's no sufficient evidence to support the original claim. All right, I'm going to write the original claim, H sub 0, H sub 1 here again. Then you can feel why why that is the formal conclusion. Yeah, original claim P less than 0.2, and it's the same with the alternative. They are the same. And the no is P equals, and we decide to fail based on our sample to reject the no. Yeah, when we fail to reject the no, means that there's a chance the no is correct. If the no, there's a chance possibly be correct, then that means you have you do not have sufficient evidence to support. So you kind of have a negative attitude toward the original claim, right? You see that? Yeah. So when you have more examples, more practice with different cases, you will feel the difference among the 4 cases. All right, guys. Yeah, I actually would recommend you ask me to include this table in the. Yeah, this actually is you probably need it for the test. All right, guys. Any questions so far? Yeah, we have to make the formal conclusion. Yeah, for the formal conclusion about the original claim conclusion, we refer to the table. Yeah, I would like you to try to make the conclusion yourself and then compare to the table. Any questions so far? Critical value method and the p-value method? No? Am I still good here with the recording? I'm muted. So quiet. Any questions? Okay. All right, thank you. I thought I lost the connection or something. Okay, awesome. Okay, now you're gonna like it. We have a calculator, right? I actually planned to go over all the 3 examples and then use a calculator. But, you know, I can just tell you because I already pre-announced it right earlier. So you know we can use the calculator to test. We can use the calculator to find the test statistic and the p-value. We are able to use the calculator to find test statistic and the p-value. Yeah. So the function we are going to use. Yeah. So this is the key you're going to enter. Okay. Yeah. Stat first. Enter stat. And go to the right twice. Select tests. And then the function we are going to select, we're going to use is a one proportion test, z-test. One proportion z-test. Yeah. So the function we are going to apply is one proportion, P-R-O-P. Z is a z-test, right? Z-test. Okay, let's select that function. And you see those entries need us to enter value 4. P sub 0, x, n, PROP. Yeah, PROP, you would see 3 options. Not equal to P sub 0, less than P sub 0, bigger than P sub 0, but mainly is the type of test, right? Is left tail, right tail, or two-tailed. And then the last row is calculate. And here's a draw. We never really use the draw. A-R-A-W, yeah. All right, so let's enter the value for those entries, for those items. Our P sub 0 is 0.2, right? Yeah, the value, the proportion we had in the claim, original claim, 0.2. Our x, what is our x? 1322. Number of successes. Yeah, this many people returned the survey, responded to survey. Yeah, n is the sample size, 6957. Be very careful. Enter those numbers. 5. Where is it? Yeah, 6,957. Yeah, okay. And then, our test is a left tail test, right? So you have to move your indicator on top of less than P sub 0, and make sure not just blinking there. You have to confirm, enter. Yeah, make sure it's not blinking somewhere else. When you go down the next line, the less than P sub 0 is still highlighted. And then you calculate. All right? Yeah. And you see right now, you should see this menu, this page, PROP less than 0.2. Here Z equals -2.08, 01, 2042. And then your p-value, this is actually the capital P, all right? P-value, not the proportion P. It's different. P-value is 0.01, 0.018757 1793. And the p hat, your proportions, sample proportion, is also given. 0.1900244359. Sometimes you need it, right? Sample size is also given 6957, right? And what we need is we need the test statistic and the p-value. Yeah, so this is the test statistic. And this is the p-value. All right, the calculator helps us to find the to find the test statistic and the p-value. With the calculator, we just save the energy to plugging in, use a formula. Yeah, if you have a calculator, actually you don't really need a formula, right? Okay, let me know, do you have the same thing with me? Applying the function in the calculator? Awesome, very good. Yeah, exactly, awesome, yeah. It's faster, right? Yeah, so I would recommend that you get a TI-84 for calculator, as you should already know how useful the calculator to your test, right? However, even the calculator help us to find the test statistic and p-value. Of course, p-value method would you don't have to draw the graph, but if the question requires you to use the critical value method, you still need to draw the curve, still need to mark the critical region, still have to see where is your test statistic fall. Yeah, does it fall in the blank region or fall in the shaded region? The shaded region is the critical region. All right. Yeah, of course, if you use the p-value method, all you need to do is to compare your p-value with alpha. Yeah, alpha is predetermined. Yeah, so that's the reason in reality, when you do your research, how big you want the alpha to be is so critical, so important. If you make the alpha big and the p-value always less than alpha, then you always reject no. So the result will not be ideal. Yeah, be careful determine the p-value here. All right, so that's the first example. That's the first example. Yeah, we really get this done. I think I really got this done in detail. Yeah, start from original claim, and then write our null and the alternative hypotheses. Based on the alternative, determine the left tail, right tail, right? Yeah. So if you manually to compute those things, you have the graph, the curve, and use the formula for the test statistic to find the test statistic and the critical value and compare, right? Or if you want to use a calculator, then you can just get those values very quickly. All right, so that is an example, left tail test. And since we have this p-value found, we want to once again to fill the definition of p-value to see if that helps you understand what is p-value exactly. P-value here is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from your sample. You have one sample only, but other people or you yourself could have many samples, right? Yeah, many samples could give you many test statistics. So here p-value actually is the probability of getting a test statistic at least extreme as the one you have right now. Yeah, based on the assumption no is true. So the p-value is a conditional probability. Yeah, I hope you can, every time you get a p-value, if you compute the p-value like me earlier, like this way, like us earlier, you want to feel the meaning of p-value again. Right? Okay, so that's the first example. Yeah, that's a left-tailed test. Let's look at the second example. In a study, or actually, we didn't check the requirements, right? Yeah, and then the requirement does satisfy. Yeah, normally when you go to MATLAB Math, you don't really need to check the requirement, but of course you need to know the requirements are satisfied. But in reality, you need to make sure all the 3 requirements are met. You don't start it when it's not supposed when the method doesn't actually apply. Yeah, we actually, I apologize, we should actually check at least this one. Yeah, but you know n is so big. N is like a 6,957. When the n is very large, doesn't matter what's P or Q, is at least B5 for sure. Okay, you can just take a glance, and you know the normal approximation requirement is satisfied. Yeah, and this is a binomial because you have success if the subject returns a survey, failure if the subject does not return a survey, and they are independent, you know, everything. Yeah, technically we should check all those things before we start a procedure. And we're going to do that here, right? Example 2. In a study of 788 randomly selected medical malpractice lawsuits, it was found that 481, yeah, so this is N, this is X. Yeah, 481 of them were dropped or dismissed. So here we see the lawsuit is dropped as success, right? So number of success is 481. Also, you see this is a so big, large number. It doesn't matter what is it. Very probably the P, NP, and NQ at least equal to 5. We'll see, okay? We'll see. Keep reading. Use a 5% significance level to test the claim that most medical malpractice lawsuits are dropped or dismissed. Okay, let's check the requirement. Simple random sample. Yeah, normally those are satisfied. Random selected. There's a binomial here. So 788 trials. Yeah, if you select the one lawsuit, that is one trial. If the lawsuit is dropped, it's success. If it's not dropped, it's failure, right? Yeah. So that's a binomial. Independent, yeah, the probability remains the same, everything. And then NP actually is X. Yeah, of course, it's bigger than 5, right? It's 481 is bigger than 5. And the failure, number of failure, NQ is the number of failure, is also bigger than 1, right? Yeah, if you have 481 successes, and you're gonna have 307 failures, also bigger than 5. Yeah, so you can quickly check all those requirements, all the 3 requirements satisfied. All right, then let's start our procedure. From original claim. Claim that most medical malpractice lawsuits are dropped or dismissed. So here, P gonna be the success rate or the dropping rate, right? The lawsuit dropping rate. Yeah, most of them. So we're gonna use P is bigger than 50% to describe the original claim. You claim most of them, so more than 50% successes, right? So P is bigger than 0.5. P is bigger than 0.5. And then based on the original claim, we're able to determine our null and the alternative. Yeah, again, null always contain equal sign. So this is our null. And how do we know H sub 1? Yeah, original claim is either equal to null or equal to alternative. In this case, since original claim is not equal to null, it must equal to H sub 1. So the H sub 1 is P bigger than 0.5. What type of test that is? Left tail, right tail, two-tailed. What type of tailed this is? Guys? Hello? Right tail, perfect. Thank you. Thank you. Right tail test. I purposely give you 3 examples. One is left tail, right? One is right tail. One is two-tailed. Yeah. Okay. So if we draw the curve, yeah, the x-axis is supposed to be the asymptote of the curve. Okay. Yeah. There's open here, but very tiny open. Yeah. Right tail. So our critical value is here, and our critical region 0.5%, right? Yeah. Then what's the area of the region to the left of the critical value? And you know is 1 minus 0.5. 0.05, I'm sorry. 0.05 is 0.95, right? And 5% fall on the right tail. That's the significance. That's the rare event where the rare event occurs. Then other region would be 95%. Anyone can help me to find z sub alpha? The function we're going to apply is inverse normal. Okay, yeah, let's go to second verse. Inverse normal. The area, please do not enter 0.05. You're going to enter 0.95. At this point, you should know that, right? Yeah, this is from previous chapters. The area has to be the area of the region to the left of the z-score you are trying to find. Yeah, so enter 0.95 here, 0.95 here. And then mu is 0, sigma is 1. My critical value in this case, how rare is rare? If the score fall around 1.644853626, 1.644853626. Yeah, if your score fall around 1.645, standard deviation above the mean is 0, right? Centered at 0. Then we see that as significantly high. See that as a rare event. See that as a rare event. Okay. And how do we find our z-score? How do we find our test statistic z-score? Test statistic. Yeah, remember it's z equals p hat minus p over root pq over n. Yeah. How do we find that and our p-value? Since I already tell you the calculator method, you probably don't want to use the formula again, right? Yeah. Let's use the calculator. To get familiar with the function we need to use to test the claim regarding population proportion. So we go to stat, go to tests, and go down number 5. On my calculator is number 5. 1 proportion z test. 1 proportion z test. P sub 0.5, x 481, n 788. 481, 788. If you use the calculator for the thing, I would strongly recommend double check. If you enter something wrong data to the calculator will not give you the right answer for sure. And also, all you need to do is to enter the data in the calculator. You must be sure you enter the right answer. And in the tail, we do right tail test. So move to bigger than p sub 0. It's going to blink in there. Make sure it's bigger than p sub 0 and calculate. And let me know what you have for the test statistic and the p-value. I'm going to write down mine, and you can compare with mine. Test statistic is z, right? We have 6.1984, 93349. P-value, I'm going to write whatever on my calculator, 2.86. 1967, and e to the power of -10. Yeah. Make sure you don't just see the beginning, you don't see the end. The end has a e to the power of -10. All right. Yeah, very, very important, that information. Okay, let me know. Do you have the same thing? Do you have the same test statistic and the p-value from the calculator? Awesome, perfect, yeah. And when you do your homework, you just need to properly round them based on the requirement of the question, all right? Yeah. So if we use the critical region method, let's see, where does the test statistic fall? The test statistic is around 6.2, right? 6.2. Oh, it's very, very big. Yeah, this is the test statistic Z. Okay, yeah, 6 around equal to, I don't want to round it, it's just 6.19849334. Means the value is like around a 6.2 standard deviation above the mean. Very extreme, very, very extreme, right? Yeah, in this case, our test statistic fall in the critical region, fall in the critical region. So are we gonna reject no or fail to reject no? Reject or fail to reject? Yeah, I believe you say reject, right? Because the rare event happens. The assumption, the whole procedure is based on the assumption that the no is true, but now the rare event occurs. Yeah, now it's rejected. Perfect. So we're gonna decide to reject no. Reject no, H sub 0. I'm going to highlight this one. Oops. Become green. Yeah. I'm gonna highlight this one, reject no. Well, if you use the p-value method, be very careful. Do not just look at 2.86 and enter 2.86. It has it has e to the power of -10. So this value is 0.123123123 2861967. It's a very tiny, 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 tiny value. Okay, yeah, you probably round it to 0. Yeah, very, very tiny value. Compared with our significance level, 0.05. Of course, p-value is low. P-value is low, no must go. Yeah, we would have the same result for H sub 0. We're gonna reject no. Okay, yeah. So look at it here. Now both methods tells us we need to reject no. Reject no. All right. Now, how are we going to make a conclusion about the original claim? Yeah, original claim is the alternative, right? If we reject no, we can say we have sufficient evidence to support the original claim. Yeah, let's look at the table, double check. The original claim is L sub H sub 1. Yeah, earlier we did the number 1, right? Yeah. So now we have original claim is the same with the alternative, and we reject no. So we conclude there is sufficient evidence to support the claim. All right, and that's the only case in which we say support, sufficient evidence to support. That's the only case we can say that. Okay. And that's example 2. Tell me, do you have any question? Example 2 is an example about right-tailed test. Right-tailed test.
I have a question. Would we also be able to request that hypothesis testing table on the exam as part of the sheet with the equations?
You mean this table?
Yes, hypothesis testing final.
Yeah. I mentioned earlier I would recommend you request me to include this table. Yeah.
Perfect. Thank you.
Yeah, no problem. As I said, this is more useful than the formula. As you can see, if you use ATI84 calculator, you don't really need a formula. All you need to do is remember the function, right? Yeah, but this table is very useful. This table is very useful. Okay, so that's second example. The example of right tail, also the example for we end up with rejecting the no. Okay, example 3, we have 9 minutes, we should be able to finish that. Suppose that in a random selection of 100 colored candies, 23% of them are blue. Yeah, so as you can see, number of successes, 23, bigger than 5, and number of failures, 77 is also bigger than 5, right? Yeah, so the normal approximation requirement is met. Simple random sample, yeah, you have 100 trials. Yeah, so all those conditions are met, 3 requirements. Yeah, the candy company claims the percentage, so this is about the population proportion. When you see percentage, yeah, today we know we are testing about P, but when you take the test, all the problems mixed together, right? You have to determine what parameter we're actually testing for. You have to identify that. So when you see percentage, when you see 23%, that is a sign we're going to test for the population proportion. The proportion of what? Blue candies. Seems like blue candy is very special. If you get blue candy, you success. If you get the other colors, you failure, right? That's what it is in this problem. Yeah, the percentage of blue candy is equal to, okay, original claim, excuse me, the percentage, the population proportion of blue candies is equal to 29%. Yeah, we always use decimals. All right, that's the original claim in a symbolic form. And based on original claim, we can find our null and the alternative. Yeah, remember null always equal, always contains equal. Yeah, so it means in this case, yeah, we have a case in which the original claim and the null is the same. So P equals 229. That's the null. Yeah. And what about alternative? How do we determine alternative? Are we gonna have a bigger than or less than or not equal to? It doesn't say bigger than or less than. If we don't see any information like that, that means we are going to have a two-tailed test. The alternative is P is not equal to 0.29. All right. Yeah, you have plenty of practice in MATLAB Math to figure that out. Yeah. So alternative hypothesis in this case is P is not equal to 29%. This is a two-tailed test. Yeah, I mentioned earlier 3 examples. First one is the left tail, second one is the right tail, third one is two-tail, right? Two-tail z-test. Okay. Very important thing is, if it's a two-tail, how do we use the significance level alpha? Right? Yeah. We're going to have 2 critical values, and they are opposite of each other. Yeah, we're gonna have half alpha here, which is 0.025, and half alpha here, 0.025. Okay, yeah, that's the special about two-tailed tests. So we have 2 critical region. The 2 tails, both of them are the critical region. The blank region in the middle, that's the non-critical region. All right. Well, anyone can help me to figure out what's the critical region? Yeah, do you agree those 2 values are opposites? Symmetric, based on the symmetry. based on the symmetry. They are opposite, right? Means they have the same absolute value exactly. So you know what? All we need to do is to do 1. Yeah, I'm gonna find the one on the left. And then I remove the negative sign. I know the positive one. Okay, so let's go to second verse. Inverse normal and enter the area 0.025. 0, 1 as mu and sigma. Paste. Tell me what you have. Do you have negative? It must be negative, otherwise means something went wrong, okay? Negative 1.959963986. And that means the positive critical region, critical value is a positive 1 around 1.96. Or we write the whole thing. 1.959963986. Okay? All right, so that's critical region. Two regions on 2 tails. Yeah, both of them. And now please use the calculator to help me to find the test statistic and the p-value. Okay, we go to stat. We have 3 minutes. We should be able to get it done. Yeah, tests, and go down. 1 proportion z-test. P sub 0, 0.29. X. Okay, guys, how do we determine the X here? How do we determine X here? It's not given, right? X would be, yeah, from the sample. This is the sample you got, okay? You have to use the p hat to multiply by n. In our case, it's very convenient, and the rounding has no problem. You don't have to round it, to be honest, because 100 is such a convenient number. But sometimes you have to round it, so be very careful. So p hat, you're going to round it to the nearest whole number. Yeah, this part actually, there's another reason I choose this problem. You don't have x given directly. You have to multiply p hat with n to find x. But sometimes you might get a decimal. You have to round it to the nearest whole number. Otherwise, the calculator tell you error. Yeah, our value very convenient. 23% times 100, of course, gives us 23, right? Yeah, again, if you get a decimal, round it to the nearest whole number. So x equals 23, n equals 100, 2 tails, so the first one not equal to p sub 0, calculate. All right, this is my result. Let's see if you have the same thing. Z equals negative 1.3222789228. Yeah, and my p-value is 0.1860754133. Guys, please let me know. Do you have the same thing? Awesome, exactly, perfect. Yeah, and let's see where does the test statistics fall. Negative 1.3 is to the right of 1.9, negative 1.9, so it's around here. So it falls in the blank region. If it falls in the blank region, we fail to reject no. We fail to reject no. If we use the p-value method, compare p-value with alpha 5%, you can see p-value is high. P-value is high, no must fly. Again, we fail to reject no, right? Yeah, when we fail to reject no, what's the no? The no in our case, the same with original claim. If we fail to reject no, then we fail to reject the original claim, right? So the formal conclusion would be, we have sufficient evidence to warrant the rejection. Oh, sorry, no, hold on. Fail to reject no. So we have no sufficient evidence to warrant the rejection of no. Yeah, it's better we look at the table here. So original claim, is no. Fail to reject, no. There's no sufficient evidence to warrant the rejection of the original claim. There's no sufficient evidence to warrant the rejection of the no. It doesn't say accept, right? You're very, very careful because we only did one test, only one sample. That would not be enough for us to accept something. Yeah, mathematics is very complicated. Yeah, you can only say you don't have enough evidence to say I'm wrong, something like that, because you failed to reject my claim, right? All right, that's everything for today. It turns out the 3 examples really fill in the whole 80 minutes. Let me take the attendance one more time before you guys leave the room. Again, I appreciate you attend the class on the holiday. Thank you guys. If you have any questions, email me. If you email me today and I have not responded you yet, it's because I had to teach in the morning and then I have an appointment with my OB and I'm very, very exhausted already. So I have not get a chance to respond your email yet, but I will tomorrow, all right? Yeah. Is this 8.2? Miranda, this is 8.2. Yeah, this section is 8.2. Okay. All right, guys. Have a good night. I'll see you on Thursday. Bye-bye.